Welcome back. In this second Zoom video in the series on blood vessels, we are going to learn about specific types of blood vessels. So I know previously we talked about arteries, capillaries, and veins, but there's actually 3 different types of arteries, 3 different types of capillaries, and 3 different types of veins. So that's what we're going to look at, the various types and why we have different ones. So when we're comparing arteries to veins, remember that arteries have that internal and external elastic lamina, which you clearly can see in the upper left is these dark purple layers, and you can see it in the bottom right, the dark purple layers in both places, and you have lots of smooth muscle between these two. So when we're comparing arteries to veins, arteries are going to have the elastic tissue. They're going to have the thicker wall because they have more muscle in their wall. And they actually have a smaller diameter lumen than their companion veins. And so we have 3 different types of arteries, which when we're talking about them structurally, we call them elastic arteries, muscular arteries, and then the smallest are the arterioles. And those are the ones that lead us into capillary beds. So talking about the elastic arteries, these are our biggest ones. So your ascending aorta, your arterial aorta, your entire aorta, the branches coming off the arterial aorta, the first branches coming off the aorta everywhere. Anything that's over 1 centimeter in diameter, up to 3 centimeters. So all your big blood vessels, your biggest ones are elastic arteries. And these are also known as conducting arteries because these are not sending blood to any one organ. These are like the 405. They're taking blood from the heart to wherever the branches, the exit from the 405 is going to be that will take them into the neighborhood they need to go to. And so elastic arteries are called elastic arteries because their wall has not just the internal and external elastic lamina, but has elastic fibers all the way through. So it's hard to see 2 discrete lamina. And so you really can tell these because on an elastic stain, you just see the black elastic fibers, almost the entire thickness of the blood vessel wall. And this is important because if you think about when blood exits the heart, it doesn't exit as a slow stream. It exits as, here's a quarter cup. Now here's a quarter cup. Now here's a quarter cup. So every time blood's being dumped into the aorta, it needs to be able to whoop and then come back to its resting stage back between these. So that's why it has so many elastic fibers. So once we are branching off of the aorta and we are blood vessels less than 1 centimeter in diameter, we are transitioning to muscular arteries, which, as their names imply, have a lot of smooth muscle. So we're back again to seeing 2 clear internal and external elastic lamina. These blood vessels are often called distributing arteries because these blood vessels are taking it to the organ or to the tissue. So this is your ovarian artery, your testicular artery. That's what these are, okay? Now, when I say these have lots of smooth muscle, what I mean is they have a lot more smooth muscle than the elastic arteries did. If you look at this, if you look in the tunica media and you start seeing, like this one obviously probably has 30 different layers of smooth muscle because you can just count how many nuclei going through. That's a classic muscular artery. Always over 6 layers, but usually 20 to 40. So if I'm showing you a picture and you're looking and you can see like the bottom right, you can see more than a dozen, probably closer to 20 layers. That's going to be a muscular artery. And so most, but not all of our named arteries are going to do this because some of our named arteries are still those bigger ones coming off of the aorta. And then coming off our muscular arteries, we are going to have smaller arteries, everything below 3 millimeters in size, all the way down to about 1 millimeter in size, small arteries / arterioles. Most people will just use the word arterial, but I think your textbook talks about small arteries and arterioles. And so we still have 3 tunics, but if you look at it, We have very few layers of smooth muscle and very little elastic tissue. You don't see a very clear internal or external elastic lamina. If you did a special stain, you would still see that there are some elastic fibers there. But basically, this is like tunica media, but these are so tiny by comparison to the other blood vessels. And these blood vessels are important because these are your resistance blood vessels. These have massive sympathetic nervous system innervation. So at times of sympathetic output, like from your adrenal gland where you have that norepinephrine, epinephrine circulating, that's going to cause all of these to vasoconstrict and massively decrease the blood flow going into your tissues. Okay, so these are really important for maintaining blood pressure and for doing perfusion of tissues. So that's it for the three types of arteries. Now we're going to talk about capillaries. So capillaries, it's not like the tree trunk where you just have one branch and now you have one tiny little branch as the capillary. What happens is from an arteriole shown here on the left, what you'll notice is you have multiple branching coming off of this. And we have what we call a capillary bed, which is usually about 100 little capillaries. And this is where the work is being done between that arteriole and that tiny little venule. So they act as a unit, they don't act independent of them. And these have a very small diameter, somewhere around 8 to 10 micrometers wide, and a red blood cell is about 6 in a diameter, so that makes red blood cells travel single file. And so if you think about the 405 highway, when you're traveling on that, if you're going from 4 lanes to 3 lanes to 2 lanes to 1 lane where you're going single file, you know how slow that goes. So this is what's good. Capillaries are traveling, have blood traveling very slowly in them, which gives ample time for the offloading of oxygen and the onloading of waste. So looking specifically at the anatomy of a capillary bed, what you will notice between the arterioles and the little capillaries come off of it, there's little smooth muscle rings at the beginning of each little capillary called a precapillary sphincter. And so we have one main arteriole that brings blood flow in, and it doesn't have a sphincter, but all the other sphincters can close off, which would make all the blood just travel through that one. But normally blood is traveling through all the capillaries, dropping off the oxygen, picking up the waste, and then showing up on the venous side to drain into the veins. But when all those capillary sphincters are closed, as what happens with, once again, sympathetic nervous system stimulation, that causes all these sphincters to contract, so no blood goes into the capillary bed. Instead, that blood will stay in that main capillary known as the mid-arteriole, right here, and continue on the venous side of what's called the thoroughfare channel. Not really important, you know that thoroughfare channel, but basically it just cuts across and it does what we call a shunt. So because there's only one blood vessel, we cannot offload nearly the amount of oxygen and nutrients as we normally would with a capillary bed. And basically we are just taking blood from the arterial side and dumping it on the venous side and only minimally changing what it is. So it's kind of like we're just shunting it across without it being able to do its work. So that's not a good thing for that tissue. So looking at the structures of capillaries, you can tell them by looking at their walls, because all capillaries, as we described, they had endothelial cells, simple squamous endothelium, and then it had a basement membrane. And so we have variations in between how cells have intercellular junctions and structures of basement membranes, because that's all there is to it. There's nothing more to a capillary than that. So that's all we can play with. And I'm going to show you the difference in the three types of capillaries. The most common type is what's called a continuous capillary. So if we're saying the word capillary, this is what we're talking about unless we mention something different. And this is the one I talked about. We have a complete lining of simple squamous endotheliums completely surrounded by a basement membrane. And actually in between the cells, the endothelial cells, we have tight junctions. So do you remember what tight junctions did or did not do? Yeah. So if you don't remember, go back and look up the function of tight junctions because here's where it is important. Okay. So this basically is going to be found everywhere except where the other two types are. So it's easier actually to learn where the other two types are rather than where this one is. But for examples of where this is going to be, your muscle has this kind, your lungs, your blood-brain barrier, it all has this type. The second type is the fenestrated capillary. With fenestrations are little holes. It looks like someone took a little hole punch or took their little pencil and poked little holes in the endothelial cell. If you notice, the basement membrane is normal. It is a complete basement membrane, but there's holes in the endothelial cells. But these holes are small. Notice their size compared to a nucleus. So they're about the size of a nucleus. So no cell can get through these, but what these holes will allow is they're like holes in a bowl. What do we call a bowl with holes? A strainer or a colander. They're going to let liquid out and they're going to keep the pasta inside or keep the blood cells inside, but they're going to let a lot more of the plasma out of the capillary. So this allows fluid and large molecules to move quickly from the blood vessel to the surrounding tissue. So we find it in places where we have lots of fluid movement, such as in our small intestine, in our endocrine gland, where we've got, in our kidneys for fluid, and also in our endocrine glands where we have all those hormones which we need to dump out of the bloodstream into their target organs. That's the second type of capillary. Now for the third type of capillary, we're gonna make the holes even bigger, and we're also gonna make holes, rips in the basement membrane. So that is an incomplete basement membrane. And these holes are big enough, if you look how big enough, you can see that a red blood cell can get through these, okay? So these holes are big enough for cells to exit. Anything can exit. And these are called sinusoidal capillaries, which are also known as sinusoids, okay? So those are synonyms for each other. And there are a few places in the body where these are found, for instance, liver and the spleen, and some other places we will talk about. So at this point, I'd like you to stop this video, do this comparison of the drawings of the three different types of capillary, come up with their names and the differences in structure. Don't forget to talk both about endothelium as well as basement membrane, as well as what can cross, what can't cross, and places where you would find them in the body. So go ahead and do that now. All right, now that you have finished capillaries and we finished arteries, we're ready to move on to the venous side. So the venous side has the lowest pressures. If we look at the pressures coming out of the heart, it's quite high, and then the further away we get from the heart, the lower the pressure. Because remember, blood flow went super slow through the capillary single file, and there's no pump down there at your toes to pump it back up. So the pressure is really low. So at rest, as you were sitting here studying, the veins contain about 2/3 of your body's blood. And so I just put a picture of this red light here, which is not blood. It's an algae that gives it its red color. So right after the capillary, we're going to have our smallest veins, and these are called venules. And this is the companion to an arteriole, the only difference being there's less muscle in the wall, and its lumen's going to be bigger because there's less muscle in it. And so it's going to look thinner. And this is the blood vessel where diapedesis occurs. So you remember the diapedesis was where the white blood cells squeeze through the endothelial cells of the blood vessel wall. So small veins, from the venules, the small veins will have a complete layer of smooth muscle, whereas immediately after the capillary, the venule may not have any smooth muscle yet. Continuing on the venous side, we then move to our second category after venule/small veins. We go to muscular venules, which, as the name implied, now have muscles. So these are up to 1 millimeter in diameter. And so they have the 3 layers, again, tunica, intima, media, and externa, but they only have 1 or 2 layers of smooth muscle. So the smooth muscle is very thin. Okay. A medium vein then goes up to 1 centimeter in size. And so it's going to have more muscle, and it's going to travel with a muscular artery. And then those will merge together to form our larger veins, which once again are just bigger, and they're going to be traveling with the elastic arteries. So one thing I want to talk about is something called a sinus that is not in a bone. So when we use the word sinus outside of bone, what we are talking about are what are known collectively as venous sinuses. They are structures that look and act like veins, but they don't have the normal vein histology. There's no smooth muscle to contract them down. There's a large lumen. It doesn't have a tunica, intima, media, external like a normal vein. And so examples where we have venous sinuses are the sinuses between the layers of the dura inside the skull. And so, for instance, that superior sagittal sinus, inferior sagittal sinus, transverse sinus, those all are sinuses. And then we're going to learn shortly, when we learn about the heart, the coronary sinus as well, which carries venous blood on the back wall of the heart. So we will come back and talk about the coronary sinus when in the lecture about the heart. So if we know about 2/3 of our blood is on the venous side, and we know there's no heart to pump it back up to our heart, how does blood down there get back up? Well, in your foot, it's too low to overcome gravity, okay? And so the way it gets back to the heart in our extremities is that those veins get squished whenever the skeletal muscles surrounding them are contracting. Whoops. So if we look at these larger veins, or larger and middle and medium-sized veins, they have valves. And the valves are oriented toward the direction of flow. So when flow is going back towards the heart, it goes up very easily when this muscle is contracting. Then if this muscle relaxes, the blood will come back down, but it catches these leaflets, which were pushed, when the blood went up, the leaflets were pushed up, and then when the blood comes back down, it gets caught on the sides, and it closes the valve so that blood cannot make its way all the way back down to your foot. It can only go as far as the previous valve. And so when you are looking at your pictures of arteries and veins, if you see what looks like a single layer of simple squamous endothelium in the middle of it, well, that's your vein valve. Okay. So what happens if you aren't contracting your muscle? Like, for instance, you're standing in line waiting for something, and you're standing, okay, and you're not moving your muscles. Well, then your blood does pool, and it does pool, and so much your blood can pool that you could end up fainting. So most people have heard of varicose veins, and I start with no picture because I want you to envision what you think varicose veins are. So when someone says, oh my God, I have varicose veins, what are you thinking? And a lot of people are thinking about these, okay? These aren't a health hazard, okay? And these, by the way, they're genetic. If your parents got them, ladies, if your mom has them, you're gonna get them. Same thing, gentlemen. If your dad's got them, you're gonna get them. Or you can get them from the other sex parents, because these are genetic. By varicose veins, we are talking our bigger veins in which the valves have been destroyed. Okay? So if the valves are destroyed, that means that more blood is going to pool in the vein, which is, and to understand what's going to happen, think about what happens to a river after a massive storm, like after a hurricane or, you know, a 3-day rain. That river is going to get super wide and can get super tortuous, and that's what happens to your veins. So on the left, you have a drawing of normal veins in your calf, and on the right, if the valves are destroyed, then blood can pool in them. And so that's a great drawing, and here are actually pictures. These are varicose veins, okay? And these are actually both men, and I put this because I want men to realize that it's not just a disease of women. So who is liable to get varicose veins? Well, there are certain jobs and things that lend you to it. Anything that destroys the valves. For instance, if you've had a bunch of blood clots in your veins, you can destroy valves. It could be from that. If you have jobs where you have to stand on your feet all day, whether it's working at 8-hour shifts, saying, would you like fries with that at McDonald's? Or whether it's being a neurosurgeon doing 12 hours of neurosurgery. So it doesn't matter what your income is, you can get varicose veins from that. Being nurses, this is why a lot of nurses do wear that support hose that you're all are thumbing your nose up in your 20s. You don't want varicose veins in your 40s and swollen feet all the time. You might start wearing some support hose to help you. Okay. So just to refresh your memory, at rest, veins are going to contain almost 2/3 of the body's blood. That lake again. So that's it for this part, and I will see you again shortly as we continue on in our exploration of blood vessels, where I think we're going to be learning about systemic circulation next.